Thanks to Lydia and Nuria for the invitation to this school. It's great that this school takes place regularly, and I think this is very valuable to kind of educate young people in foundations. And I also wanted to thank the two, not only for organizing the school, but also for the scientific contributions to what I'm going to present, because both of them were involved in many discussions over the years about agents and their roles, as well as Ladina, who is also here, who is currently working on this subject. And so there is influence by all of them in what I'm saying. So I will start with an extremely simple experiment, and then we will build up to more complicated situations. So if you at the beginning think this is just trivial, then that's somewhat intended, but let's just see how it goes, and I will try to keep this interactive. So let's first think about an experiment where we just want to measure a spin without destroying it. And I could draw this as a circuit. And by the way, whenever I draw circuits, I will use the convention that time goes from top to down, which is, by the way, for those used to relativity, the opposite of when we draw space-time diagrams. But, so it's sometimes confusing in that way, because in particular, what I want to do maybe tomorrow is to compare these experiments, or these kind of quantum thought experiments, to relativistic experiments where one draws space-time diagrams, and I will come back to this convention clash. So let's suppose we have a spin particle, which I just draw here as a wire, and maybe you could also give it a name, S, for the spin particle. Now, if I would like to measure this non-destructively, one way I could do that is to say I have a second wire. You could think of a qubit, which I initialize to the state 0. And if you want, you may also think of the spin as just written in a qubit basis. What I mean by that is we take something we call a computational basis, 0 and 1, and then it's just a qubit, and then the general state of what comes in, if it's in a pure state at least, is can be written like this. And then we do a kind of controlled NOT operation on this additional system, and otherwise don't affect the spin that we want to measure. But now we can measure this this additional system, this additional qubit that we introduced, let's say, for example, in the set basis. So by the set basis, I mean the computational basis, and we get an outcome here. And let me label this outcome by little set. So that's clearly something we can do. I hope the notation, the circuit formalism is clear. So what this means here is just a control NOT. So if this is 1 here, we will flip that bit here from 0 to 1. And if here we have a 0, we will not do anything here. And so then you can easily see that if I now check whether this is 0 or 1, this tells me whether the spin was 0 or 1. And I will now use this convention. I will not talk about up and down, just zeros and ones. So the spin is more like just to distinguish it from this additional qubit. Now we could ask questions that like we could answer in a very basic quantum information course about circuits. We could say, let's now label the state of the qubit here as phi, and let's call it phi s, because it's only about the qubit s. And now, clearly that state will depend on the information I got by looking at this measurement. So I could make some statements, for example, if z is equal to 0, then I know, then I can say something about the state of this qubit. So just to make sure we have an agreement on the notation, what could I say about the state? What, in this case, what would be the qubit state? Everyone see that? It would be great to get some answers, just to, as a double check that I didn't miss up, or that we have agreement on the notation.
The NOT is activated if it's 1, right?
Yes, right, that's correct. So the NOT is activated if it's 1. So 0. Yes, so that would be 0. And then I could, of course, do the same with if z equals 1, then phi s, I think it's now symmetric, 1. Yes. Thanks. Okay, so that's, I think, the agreement we can have. Or who would disagree with that conclusion? Just to be sure. Who thinks that I should do something else? Just to be very clear. Or let's just do a voting, because it's really important for later. Who agrees with that? Okay, so we have basically, I would say, more or less 100% agreement. Who is unsure? Okay, no one is unsure and no one was against. Okay, good. So that's approved. Okay, now we go to something. That's how we do physics. Yes, physics by democracy. Now, okay, let's now go a little bit further and say, actually, this situation, maybe, I mean, I would also agree this is correct, by the way, so this was not to trick you. But nonetheless, someone could come and say, isn't this measurement device itself also a physical system? So what happens if we model this more carefully and assume that there's something more detailed going on in this little box that I called the set measurement? And let's then reanalyze the situation. Someone could restart on a new piece of paper, and I will do this now relatively fast. So what I would draw is basically the same start. So we have this spin, which I've drawn like this, and then we have this knot, so that's still the same. So I'm not changing anything in this first stage. The only thing I want to change is this. Here I before had this measurement device set. So now I say this is maybe a larger, if I look inside, I draw it a little bit larger. There's some box, and maybe what happens in this box, if I do a measurement, is something, somehow or interacts with other things. So for example, a measurement of a photon, the photon hits a plate and then lots of electrons are ejected, and then the electron current is measured and maybe amplified. And so one way to do that still in an abstract way is to say maybe there are lots of other systems like the electrons on the photographic plate, and now this thing again controls all of them in a way. So I mean that's still of course an abstract viewpoint, but it should be kind of closer to what's going on if I look in detail what's happening in such a measurement device. So this don't need to be, by the way, controlled knots. It could also be some other controlled unitary that just changes the state of the system. And so we have this situation, and I could still assume maybe these things were initialized here. So here I have maybe an initialization stage where they all initialize to the state 0. So I could now say this is what the measurement device is doing. But now to make a statement from that viewpoint, I still need to say somewhere from this more detailed viewpoint, I look what happened in this device and make another measurement. Let me now, this is now outside the device. I need to look at this and look at one of these electrons that was ejected and check what the outcome is. So I call this also set, but I put now a label because I say this is now the analysis from a different viewpoint. Let's call him or her Charlie. So just to briefly make the connection. So before I had this picture, and here we'll now say this was Alice, so I will put a little superscript A. That was the outcome that Alice saw. And I'm now saying someone else analyzed the same situation, just making more explicit what happened with the measurement device, and what was this set before is now this big thing, and what came out of set was still a quantum. So Charlie modeled everything, the whole measurement device, as a huge quantum system, but of course to still access the result, he still has to, or she still has to say, we now do this final measure, or I look at one of these wires and look at the result. Now what are Charlie's conclusion? Charlie's conclusion could be written in a similar way, because now I have just a more... Okay, so what I discussed before, these are really basic examples, just the measurement, and you see there are interesting questions if you consider the agents as part of the system, which leads me to the question, what is an agent? And I will not give you an answer in the sense of a definition of what is an agent. However, what I want to do is to give you some criteria that are necessary for the treatment of agents in quantum theory. So you shouldn't, as I said, understand this as a definition, because if you talk about agents, there's only notions coming in potentially like consciousness, as already in Wigner's paper. Wigner talked about the consciousness that may be relevant and so on. And unfortunately, I don't know anything about consciousness, so I try to avoid this. And we can safely avoid that if we say, let's not attempt to even define it. Let's just see what are necessary conditions for an agent and just consider them. And so what are necessary conditions that I want to impose? It's still kind of a choice in my modeling, but I hope you agree that it's a useful modeling. So the idea, the overall idea behind all this modeling of agent is we want to model us. So that's the most important starting point. It's not some hypothetical thing. It's at the end we want to model us. So we can ask, what is the aspect that is now relevant in these considerations about us? And the aspect that was obviously relevant is I'm a user of quantum theory. I did calculations with quantum theory. I applied the formalism, and I made, in a sense, predictions. I mean, now not explicitly, but it was implicit when I said the state of the system S is a zero state. What I meant by that implicitly is if I went there and applied now a measurement in the set basis, my prediction would be that of quantum theory with the Born rule that with certainty the outcome is zero. So therefore, I want to impose on an agent this like ability to apply physics. But now we have, first of all, a kind of problem, because as I pointed out, if I'm really careful, and Lydia reminded me before of that when she asked, who is the referee? I have to say, I want to define an agent also from my perspective. But I'm now myself an agent. So what I can do is to say, let's assume, I mean, I'm an agent, I want to model agency, but maybe there are other agents in the world. And so what I could do is say that I postulate, or this is kind of a, I mean, these are also, you can see it as a definition, and later when you use it, it's a postulate that this definition has something to do with the world. But that if I look at the system that I perceive, some of them are agents, like you, for example. And now I can ask, how would I describe such an agent from my viewpoint? So from my viewpoint, an agent is now an information processing system that takes as input interactions with other systems. So you interact with the world. You are also physicists. You read off measurement devices. And then you act in the world. And because you're a physicist, you can also make predictions. You can tell me, I predict now that this outcome of that measurement will be zero, for example. You could communicate that to me, or you could write this on a piece of paper. So from my viewpoint, there are other systems that act as agents. And I could then even think about a recursion. I would also assume, because you are, I mean, I want to assume that these other information processing systems that I call agents use the same rules that I'm using. So I'm only interested in them. And so this means you would also again describe other systems as agents, maybe me and so on. But the important point is that from this, I can now turn this into kind of a technical definition. I can say an agent is just a system out there in the world, but it's a special system. It's a system that issues predictions according to certain rules, which I think of the rules as of quantum theory. Now to be more concrete, and after having given you that definition, I could say there are actually also other agents that satisfy this definition which are not humans. For example, a computer that I just programmed with the laws of quantum theory, and maybe this computer should also have some connections to devices, so it's maybe a computer in an experimental lab that can access certain experiments, and it can also has a monitor where it shows its predictions. And so this computer is equally an agent according to these necessary criteria as a human agent for all the considerations that I want to make. And so what I said at the beginning is just to tell you, I'm not implying with that we are just computers. I'm just saying these necessary conditions that I want an agent to fulfill are equally well fulfilled by a computer. And it makes our thinking, I guess, much easier from now on. Whenever I draw a little agent, you think actually of a computer.
Can the computer be quantum? What I mean by that is,
Yes.
like, I mean, the predictive information
Mm-hmm.
that comes out from an agent has to be classical or can be also quantum?
Yeah, this is a very important question I will come to. So let me answer it even now already. But so the question is that computer quantum? So indeed, I now want to make an additional or invoke a principle. I call this a principle because it's something that may be disputed by some. For example, Wigner in his original paper would say this, or would not see it like that. And my principle is that an agent should be, at the end, also a system like any other, a physical system like any other system. So it follows now from this principle that if I'm modeling the world using quantum theory in the usual way, so now I should maybe explicitly say not in the collapse theory or so, just according to standard quantum theory, but assuming that it applies to everything around me, then in particular these systems that I now call agents, these computers are also quantum objects. So in that sense, it's an agent is a quantum object. Now, the question is now, under which conditions can I make use of the information that an agent, for example, communicates to me, and I will come to that. But a priori, it's a quantum object. So, which doesn't necessarily mean I need to model all the details. So, I should point this out. So, when I say I'm now describing, I'm regarding you as agents, I don't want to imply that I really now go to the level of detail where I can model all degrees of freedom of you explicitly. I could also say, if I'm only using like classical information about you, now classical means in the quantum information sense. So what I mean by that is basically, if you think in the picture where there is a more detailed description, there was enough decoherence and so on, so that the degrees of freedom appear classical to me, then I can model you as classical. So what I'm doing now in practice is, if I knew that you would all apply the same rules of quantum theory, which according to the survey I took before you probably do, because I would also say both Alice and Bob are right, and this depends on how we apply quantum theory. So I would say you are agents, and I still model you classically. I just model you quite abstractly as someone who makes calculations and not you, I mean, all the details. So that's still allowed. So I'm not saying I have to model all the details, but I consider you as a system as anything else, and also the computers in that way. So, yes, so that's the point. So think from now on, when I talk about agents, about information processing devices programmed with the rules of quantum theory. This has now two advantages, thinking in that way. The first advantage is that this doesn't kind of confuse concepts that we may intuitively have about consciousness or like perception, that are also relevant maybe, but it doesn't confuse them with the technical considerations we want to make. And the second thing, which is equally or maybe even more important, is that it forces us to think of physics, of the laws of physics, as being made so precise that we can program a computer with them. Because often people in these arguments say, oh, shouldn't we do now this or that because there was this guy or there was this outside system, we now should apply the rules in that way. And then I would say, yes, but what's the rule? How would you precisely describe the rule that makes a computer that is now programmed with that do exactly the right thing? And here is, for example, the discussion about the Heisenberg cut, very important. I told you before that we can move the Heisenberg cut according to von Neumann. And so if a computer is now programmed with the rules of quantum theory, he has to choose the Heisenberg cut somehow. So you can either say, make somewhat a random choice or so, and it's not relevant, but if you think it's relevant what choice he makes, you have to program a rule and say the Heisenberg cut has to go through that part and so on. So that's, these are the important aspects. So I really want you to think of agents from now on as computers, programmed with the rules. Now, what are the questions now. So the big question I want to answer is, if we do that, can we actually come up with a consistent use of quantum theory? Because we have now agents who look at other agents, and these agents ideally should be able to at least exchange some information with each other. So what I want to do is to say, if we have now such a scenario like before, we have Alice and Bob, what are rules that allow them to, I would call that, collaborate? So, for example, Alice can tell Bob something, and Bob should be able to use that information that Alice tells him in such a way that we model what we are actually doing in practice, because in practice we do collaborate. You're not reinventing all of physics. You're reading a textbook about quantum theory, and then that's a communication, obviously. So you take information from other agents and use it to make predictions. So the question is, how can we incorporate that kind of agreement between agents and still remain consistent in situations as we had before, where we have two different state assignments from different viewpoints? So the question is, are these things compatible? So we have seen in the example in the hour before that sometimes agents assign different states to systems, but on the other hand, we also know that we collaborate, so we think that what others do is correct. So we cannot just say, so the solution to say everyone just has his own opinion and make some state assignment is completely unsatisfactory, because it doesn't tell us why it works that we collaborate in physics. So we want to find this kind of or the interplay between agents and see whether this is possible. So that's kind of, and the big, in my opinion, this is a very important physics question, which one should ask for all physical theories, not only quantum theory. Can we consistently model agents within that theory? What I mean by that is what I said before. So the summary of that is, we model agents as part of physics. So they're physical systems as every other physical system, so they obey the same rules. But in addition, they are programmed with the rules of that theory. And now the question is this consistent? And if it was not, then we are in huge trouble, in my opinion, because then we don't have a consistent way to understand how we actually operate, because we are physicists in this world, and we do interact, and we use quantum theory, have no other theory. So that's the starting point, basically. Now let me say, just as a brief remark for those who know about it, that Maxwell's demon is actually a kind of test of that type in thermodynamics. Because in thermodynamics, you can ask yourself, what happens if you have a little demon that controls a gas? And then you have to see the demon itself as a thermodynamic system to really understand this. Otherwise, you run into the paradox, which was Maxwell's demon paradox. So there, in a sense, the resolution is really to take this viewpoint, to take this principle that I mentioned before serious and say agents are themselves physical systems, so they have to be described within the theory, and we should ask ourselves, does the theory allow us to do that consistently? And in thermodynamics, at least in that particular example, this is the case. But I will not now discuss this example. That would also be an interesting example, but we have to focus on other things. So what I want to do now is actually to show that at the moment, with the current understanding of quantum theory, we have an open question here, a big open question, in my opinion, because there is no satisfactory solution to that question whether we can consistently do physics. And in order to show you what the problem is or what this question is, I would like to derive a paradox, or derive, in a sense, show you a paradox. And a paradox is the following. So let me first tell you what I understand as a paradox. So we will also always take the viewpoint of agents, to be careful. So whenever I don't do that, remind me of this. So we have an agent, Alice, and Alice is using a theory. So think of now of the computer. I cannot draw computers. So she's using a theory and having some thought. So this is what's going on in this computer. She has some argument, which I don't write down, but maybe she comes to a conclusion about the value, like before. She comes to the conclusion that the outcome set is equal to 0. But now it could be that the same agent, Alice, still uses her theory, but she uses the theory in a different way. Maybe the theory has different rules, and you can usually try to arrive at the conclusion via different paths. So she does some different derivation, and she comes to the conclusion z is equal to 1. then clearly Alice should say this rules, this set of rules I'm using that I'm calling my physical theory is problematic. I arrive at two contradictory conclusions, so that's not a good theory. And so what I want to show you is that if we take quantum theory and supplement quantum theory with some almost minimal rules of how agents interact with each other, then we indeed arrive at such a paradoxical situation. And so that's then the open question. The open question is how to circumvent that, and I don't have an answer, but that's why I think it's great to have such schools, because there are many young people who can probably find an answer during their career. Now, as a preparation for that, I need to talk about, for a quarter of an hour, about something completely different. I mean, it's still quantum theory, but it's about games in quantum theory. And I will not do game theory now. I think we have some specialists in game theory here. Gisela, who is also here in the back. But it's not game theory. It's about a formulation of certain problems in quantum theory as games. And I'm just doing that in order to be precise. And what I will do is I will now ask you a question about which is somehow related to Heisenberg's uncertainty principle. So let me introduce that as a game. So suppose you are a player playing a game, and it's a single player game. So you are the player, and there's only a referee. And the referee judges whether you won or not, and then you get a prize. I mean, later the player could be more than one agent who collaborate, but for the moment it's just you, let's say. So in this game, your task is the following. Send a system S, think again of a qubit, to the referee. You can choose that system, prepare it in any way you like, send that to the referee. The referee chooses a random value, independently of that system. It just chooses a random value between 0 and 1. So that's what I indicate by this little r. So that's randomly chosen, let's say according to the uniform distribution, if you like, from your viewpoint. Now he tells you the choice. And now what you have to do is to send a classical bit G. So G is a bit, 0 or 1, which is supposed to be a guess for the outcome of a measurement that the referee does on the spin. And now you win on the following condition. So if, and this depends on R, so if R is equal to 0, it's a different condition, and if R equal 1, it's another condition. So if R equals 0, then you win. So in that case, the referee applies a set measurement to the system S. So here he got the system S, he now measures it, he stored it, and now he measures it, or he could have measured it before, that doesn't matter so much. And he gets an outcome little set. If R is 1, he measures the spin S in the X basis and gets a little outcome X. Now you win if your guess is equal to Z. Here you win if your guess is equal to X. Okay. So, you see, you have to kind of, I mean, I hope the game is clear. You just send, let's say I'm the referee. You send me this qubit, I flip a coin, it's 0 or 1, I tell you it's 0, then you know I'm going to measure it in the Z basis. You send me the outcome of that measurement, or what you guess is the outcome. I do the measurement and check whether you were right. So, who thinks this game, okay, maybe let me make a survey again. Who thinks you can always win this game with certainty? Okay.
I know S, right?
Hmm?
I know S.
You prepare, yes, you can prepare S. That's part of it. You can cleverly prepare S. Okay. Who thinks it's only 50%, or the probability of winning is 1/2? That's a kind of reasonable choice in such games. Okay. You think it's 1/2, yes. Okay. Another canonical choice is 3/4. Who thinks it's 3/4? Okay. Then what are the open choices left? I think who thinks it's between 3/4 and 1? Who thinks it's below 3/4? Okay. okay, who didn't vote? Okay, so let's say, yeah, there's obviously a wide range of opinions, plus those who don't know. I mean, it's of course hard to find a good strategy, one could think, but actually there is a very simple strategy to win with probability 1. If you look at this game, I didn't tell you that you cannot, in your lab, keep another qubit. So what you can do is, you put here a qubit Q, entangle that with this qubit S, and what you send to the referee is just this entangled, is this S which is now entangled with Q. Now you just wait, so that's waiting here, and once you receive R, if R is equal to 0, you measure your Q qubit in the Z basis and compute the guess. If R is equal to 1, you measure in the X basis and you get the guess. And if the qubit is entangled with a Bell state, with that Bell state 0, 0 plus 1, 1, then, of course, if the referee chooses Z, if R is 1, he measures in the Z basis, you measure in the Z basis, you get equal outcomes. The same is true if R is, so this was if R equals 0. If R is equal to 1, both measure in the X basis, and you probably know that this Bell state has the property that in the diagonal basis, which I indicate with a bar, it also has this form. Oh, sorry. So even if in the case R equal 1, when both measure in the X basis, you also get the same outcomes. So you always win. Okay, so, but this shows that if I wanted to invent a game which illustrates the uncertainty principle, I actually failed. So let me revise the game and try to see whether I can give you a game which you cannot win. Okay, that was trial 0. Let me now make the second trial. You again send, so this is a new version. We will now consider this version. Forget the other one. This was not a good game to show something of quantum theory, if you can always win. So now the game is a little bit different. You have to, so the referee again chooses randomly between 0 and 1. But now he doesn't tell you which choice he made. He just tells you, please send me predictions for both possible measurements. And now you, if R equals 0 or R equals 1, you have two winning conditions. Again, if R equals 0, he measures in the spin S in the Z basis. If R equals 0, he measures the spin in the X basis. Now, in this case, you win. So you win if Z equals your guess Z bar, and in the other case, if the outcome X equals your guess X bar. So you kind of here give guesses for both possible measurements, and then you win if the corresponding measurement guess that is actually corresponding to the measurement that is carried out matches the outcome. Is the game clear, or are there any questions?
So Z hat and X hat are guesses again.
These are, yes, I should say. So these are guesses. So this is in 0 plus 1, as you write here to the 2. So Z and X are both zeros or ones. Who thinks we can win this game with probability 1? Yeah, okay. 1. Do you have a strategy to win it with probability 1?
Well, assuming I can do the same game, like meaning I can entangle the two it's one, I can construct a POVM that actually measures in some way both X and Z. Like, even if it's not perfect, it's probably not probability 1, but it's pretty close.
Yeah, so it will. So the strategy you're describing is a good strategy, and it was analyzed. And if you choose the POVM, so I think your strategy is similar to the one before. So you entangle this and measure here cleverly. But now your measurement should give both X and Z, so it has to be a POVM, as you pointed out. This has probability 0.86. And yeah, for those who are interested in the details of this calculation, I can refer you to a paper which you find the reference actually in the paper I wrote with Ladina, who is here, and I give you the reference to that later. But so there's a calculation that shows that. And this is actually the best strategy. You don't even have to entangle. You can also kind of, once you do this POVM, calculate the state that you have to send that is post-conditioned on that and so on. But indeed, so the probability is not 1, it's 0.86. So this illustrates that it's, if you compare the two games, it's very similar. Like on the right-hand side, the referee does almost the same, you see here. The only difference is that the player got some additional information R, whereas here he has to output both cases. So details really matter, and that's why this is just to illustrate that if you do like statements like, the uncertainty relation implies that you cannot know X and Z at the same time, then you should ask back and ask, what do you precisely mean? When do I have which information? When don't I have at which point do I need to answer a question? So you have to make it operational, that's the point. And this game here that I showed you first shows that you can, in a sense, know the outcome of the X and Z measurement at the same time. Namely, at this point, before you have measured, you can still choose how to measure and extract both information. So in a sense, in your quantum memory queue, there is the information about both. So this is only to raise awareness of really being precise and operational. And games are a very nice way to make things very precise, because then you have to win, and it's operational. So what I will show you in the rest, maybe not today, but also tomorrow, is a strategy to still win this game with certainty. However, I just told you the best strategy here has 0.86. So this will be a paradox then. So the idea is the following now. Let me return to this slide I had before. So I told you this, we come to two different conclusions. Now, what we will actually do is to have one such bubble. Let's say, let me make it a bit larger. It's basically the bubble saying that if we just use quantum theory and use the calculations that I mentioned, actually are in a paper, as I said, by Renner about quantum theory, you find that P win is smaller than, actually it's precisely 1/2 plus square root over 1/8. And this is strictly smaller than 1. And now I will give you another way of reasoning, which involves reasoning via other agents. So it will also involve quantum physics, but involve some consistency between agents. It will involve some assumption about how we can communicate with other agents, and this will lead to the probability, your conclusion that you win with certainty. P win is equal to 1. Now, this is almost a contradiction in the sense as above. You can somehow repeat this, and then you see here you win with certainty. Here if you repeat it, you will certainly lose. So you can make the certain statement that after finitely many rounds you will lose. So we have in that sense a contradiction then. Okay, there was a question somewhere here. Yes?
I don't understand how we get this probability of 1/86, the second game, because the player can only randomly choose in which basis they measure, right?
Mm-hmm.
I mean, you have no information of the referee, so
Yes.
to me it seems to be 50-50, no?
Yes, so thanks for the question. So I just told you there is a proof with maximum that. Now it can actually be achieved, and the way to think about this is the following. This is not, so for us the only relevant thing is that it's not larger, not that it can achieve. But of course it's interesting to ask, how can it be achieved? And so let's say the kind of trivial strategy which would achieve 0.75 would be to just say, let me here just prepare a spin in spin 0. And then, of course, the guess for Z hat is clear. It's just a 0. And here I just put the random value. And now with probability 1/2, the referee will choose to measure Z, and then I will always win. With probability 1/2, he will make a diagonal measurements, and I will win with probability 1/2 conditioned on that choice. So in total, I have 0.75. So I'm already at 0.75. Now what you could imagine that this is now something you have to calculate. I don't have a good intuition for that, but you can imagine now you made here a state 0, you prepared a state 0 so that you can make a prediction with certainty about Z. If you now rotate this state a little bit, you can still make very good predictions about the set measurement, but you also can now make better than random predictions about the X measurement. Now it happens that these two things don't compensate each other. Actually, the way you improve your guesses about X bar is larger than the way it decreases the prediction about Z bar, as long as you don't rotate too fast. And it turns out that the ideal state is somewhere exactly in between the zero state and the zero, let's say, the diagonal state. And then you can actually do the calculation. If you take the state in between and just calculate the guessing probability, you will find that it's that value. The harder thing is then to prove that it's optimal. But does this answer the question? Yes?
Just to clarify, is this like analogous to the CHSH game?
I mean, here, let's say, the way I now describe the strategy here, it involves some entanglement. But actually, if you just, the optimal strategy, as I just described it, only requires one system, so there's not even entanglement. So in that sense, it's not directly related. Of course, the basis choices and so on, there are similar calculations that occur, but like here it's really just, what is the optimal, how do you choose a state so that two different complementary measurements with high probability give the same predictable outcome? Any other questions about this? Okay, so as I said, the goal will be to tell you how to win. So what we will do is kind of to find a way to prove that the winning probability is 1, which of course contradicts then this, and then we have derived the contradiction to quantum theory, which of course means that some of the assumptions entering here are problematic, but it's then really problematic because these are assumptions we really don't want to give up. And in order to tell you what these assumptions now are, let me proceed one step further and say something about communication between agents. So let's suppose we have here an Alice who communicates to Bob. So for example, she communicates the value. So she sends a little piece of paper over, and on this piece of paper she says, I made the prediction that Z is equal to 0. So maybe there's some measurement going on somewhere. Let's say there's some spin like before and some outcome Z, and she talks about this. Let's suppose this is a measurement device that is accessible to Alice, and it's also, let's say, accessible to Bob. And let's say Bob is the receiver of this message here. And Bob can also check this for the moment. Now, of course, when she sends that, the assumption is, again, Alice is a computer who used the rules of quantum theory. Maybe she knew that the initial state here is 0 and that this is a Z measurement. And so she did some calculations and arrived at this conclusion. She arrived at the conclusion Z is equal to 0. Now, let's suppose Bob doesn't know the initial state here and he cannot directly do this calculation because Alice has this information. But he now reading the message of Alice, he knows at least one thing. He knows that Alice only, because he received the message, he knows that Alice knows that Z is equal to 0. I mean, that's a natural thing. That's what, if you communicate to me, the least thing I know is that you knew what you told me. Or at least, I mean, assume, as I said, we are all agents now programmed with these rules, so you're not cheating me or anything. So if I'm the receiver, I know what you knew. But now, normally, what I want is to make use of that information. And here comes in the important point that when I defined an agent before, I assume I made it explicit to say that you're all programmed with the same rules. So it somehow means I would have done the same if I had access to the information you have. And therefore, it would be very natural for me to conclude now that, so that's still me, to conclude that indeed, if you came to the conclusion Z is 0, actually the conclusion is Z is 0. So that's a step, and that's, however, a non-trivial assumption, which somehow, however, can be understood as meaning that we even agree what we mean by Z. Because, and that's returning to this question that was raised before, what does it even mean to talk about the same systems? So if, for example, I'm saying look, there is this church bell ringing now, and we talk about that church bell. Clearly, the sound waves, that the particular excitation of the atmosphere that reaches my ears is a different one from yours. So why do we talk about the same church bell? We kind of have this understanding it's the same church bell we are talking about. Because if it's, and the reason is because, for example, if it stops ringing, we both agree it stopped ringing. If it rings again, we both agree it rings. So we kind of make experiments beforehand. I mean, we do that in our daily life. A baby, when it grows up, then it sees things and sees how the mother reacts or the parents react. And so we somehow make a system identification. For me, it's the same church bell as for you, despite the fact that I'm actually interacting in a different way with it. And so this is the same here, and it's also relevant for the examples before when we had Alice and Charlie. They both measured the system, but they had different, let's say, at the end, the last input that was measured was a different one, but they agreed. And so here, you would say, even talking about this, like the fact that both of them call that value set, they have here this system in mind and say this is set, means that if Alice thinks this set value is 0, I should also mean it's 0, because otherwise we are probably talking about a different system. So that's kind of the reasoning behind. So, and I call this assumption C for consistency, but you can even understand it as just an assumption about identifying systems. We can agree on certain systems being the same. And the reason why I'm emphasizing that so much is that, at least in my opinion, there's almost no way we can get rid of this assumption in order not to lose any ability to communicate. Maybe we can restrict it to certain situations, but somehow it's an unavoidable assumption. Without that, we are in a completely solipsistic world. And that's why it's, in a sense, for me, worrying if I tell you that if I now have this situation that if I just use quantum theory and this additional assumption, I get a contradictory conclusion from the one I get with pure quantum theory. So that's kind of the overall plan of what I want to do in the remaining time to show you how this arises. Let me briefly, as I have this picture, emphasize another point. So I now told you what C is. C is just this assumption, this arrow here. So that's the assumption C. And I will use it many times in the rest, certainly tomorrow. But the other thing is this assumption Q. I now take it to be the one where we kind of, I think a majority of us agreed on, that in the beginning I showed you two analyses of the same experiment from two different perspectives, from Alice's and Charlie's and also from Bob's. And we all agreed that all of them are correct. I mean, you don't have to agree on that. As I said, the many world would not agree,